আগের দিনের থেকে এনিথিং?
না স্যার, আর কিছু নেই স্যার।
আচ্ছা, okay. So last time I think where I stopped, we partially described the finite dimensional irreducibles,
হ্যাঁ
and I think asked you to do some computation so that you finish that description of the finite dimensional irreducibles,
হ্যাঁ
right? Okay. So, so what you had to compute was, one of the things that you had to compute was x, this quantity, which was q number j, y to the power j minus 1, and then k followed by 1 minus j, right?
হ্যাঁ
And then after doing the computation, what you derive is that you have these two families of representations, one
পজিটিভ আর নেগেটিভ।
so here the action is like this: phi k vj is q to the power m minus 2j vj, and for this it is
মাইনাস
vj, and then phi y is right shift. When you reach the end, it takes you to 0. And phi x was so this is phi x, the formula came out of your computation. So phi x was what? Phi x was
হ্যাঁ
this is for j 1 to m and 0 j equal to 0. Similarly here it's for j between 0 and m minus 1 and 0 for, and only difference with here is here you get a minus sign. So one is phi k, there is a minus sign there, and in the expression for phi x also there is a minus sign you get for phi m minus. So here there is a bit of difference with the classical SL2C. For classical SL2C, you just have for each dimension m, each m, you have exactly one irreducible in dimension m plus 1, and there it was this. And then phi y is almost identical, and phi x, instead of the q numbers, you have usual numbers for the same expression. Okay. So that these are irreducible, that the proof is similar to the classical case, right?
হ্যাঁ
Okay. did you look at the notes? I mean, the next part.
না স্যার এই পর্যন্ত দেখেছিলাম
Okay, okay, fine. So
ওই জেনারেলাইজ আইগেন স্পেসের আগে পর্যন্ত,
generalized eigenspace.
মানে এই পাইকের করেসপন্ডিং তো এখানেও জেনারেলাইজ আইগেন স্পেস পাওয়া যাবে না?
Okay. So before that, so there is another equivalent form that you can find these irreducibles is, I mean, there can be several. So any change in basis you make, the coefficients, the operators will can appear a little different. But one other form in which you may face often, you may encounter often, is this. So you still have an m plus 1 dimensional space with say basis Vj. So pi k Vj same, similar to what I had written down for, I think, classical case. So pi x Vj so in the earlier, on the left side, pi m plus, the expression is this V j minus 1, right? And 0 if j equal to 0. So here it's a little different, the coefficient is this to the power half. And this is, so here also there is a change. So this is this to the power half times Vj plus 1 if 0 less than equal to j less than equal to m minus 1, and 0 if j equal to m, and a corresponding looking representation where you will have a negative sign here and a
then pi x
negative
would be
sign here, pi x. So this is just the earlier representation. If you make a change in basis, and the basis change would be
similar,
the earlier Vj divided by this q number j factorial or some such change. So it's not a very non-trivial change either. You just replace the Vj's by an appropriate multiple of them themselves, then you will get these numbers. So next, main goal next is to prove, like in the classical case, that any finite dimensional representation decomposes as a direct sum of irreducible representations. That means direct sum of these two families. Okay. So suppose you have a representation so what is a weight space of this representation? Weight space is basically an eigenspace of pi k.
Okay. Generalized eigenspace or
no, eigenspace.
Okay.
So this is definition.
Okay.
So any eigenspace of pi k we will call an weight space. Okay, so this definition here I did not mention finite dimensionality. Now we'll start with a finite dimensional representation. Okay, so if we look at the operator phi k now, or any operator for that matter, this is a finite dimensional space, right? V, and it's a complex, so that is also there in the background. The concerned field is the complex field. So phi k is a phi k is a matrix over complex numbers, right? So it has an eigenvalue.
Yes.
So there would be weight spaces. That much. I mean, for that we don't have to do anything extra. There would exist weight spaces. So the first step, what we will do is we will prove that in fact V is a direct sum of weight spaces. So this would be the first result that we will prove. Go to the next page first. Okay. So in other words, what we want to show is that the operator pi k, the matrix pi k diagonalizes, is diagonalizable. And one way one can show that is that the minimal polynomial has linear factors. So what we want to show is that okay, so if we can show this, then it would follow that this operator is diagonalizable. Okay, now in order to show this, so this part will involve a little bit of computation. So the entire computation I'll not do here. It's in the notes, but before that, again I'll just leave out exactly the computation part, which you can do yourself.
Okay.
So again, basically it would make you more familiar with this Q numbers and Q commutations, etc. So what we'll do is so we define this quantity and also define this quantity small h r, which is okay. So that means what is h naught? H naught is 1, it's there in the definition, built-in definition. And what is HS?
R equal to S for each
So this is
minus S plus 1 base n.
so it's the same expression. It's R replaced by S, and what is this? The H0 is 1, pi 1, okay, just a minute. I'm mixing the notation a little bit. So we have started with a finite dimensional representation. In fact, I skipped a step, that's why I'm slightly getting confused. Yeah, the step that I skipped is, okay, once you have a finite dimensional representation, okay, maybe I'll delete the left part and make some space then. Right. So here, I mean, I forgot to specify what is this S. So S is such that this is 0. So that is something that
Least S or any S.
least any S would do.
Okay.
I mean, once you get an S, you can work with the list such as, but any S would do. But the point is to show that there will be one single S for which pi y to the power S will be 0. Okay, so this in the classical case we saw here, I don't remember. Let me just last time did we?
It is also for finite dimensional. So for that case, it should be 0 for some S.
Sorry.
It should be 0 for some S. Otherwise, we get a infinite number of basis element.
So right. So last time it would follow from that statement that if you start with an eigenvector for pi k and start pushing it with pi y, then you get eigenvectors. You generate eigenvectors of pi k with different eigenvalues. So that means so the proof would be I think we proved this in the classical case. One thing we know is that the space would be a direct sum of generalized eigenspaces. Then you can employ this argument for generalized eigenvectors for pi k. Right. This is how we proved in the classical case that pi y and pi x are nilpotent. It is the same here. I mean, right now we have not proved decomposition into irreducibles or decomposition into eigenspaces. So, but what we always have is, since it's finite dimensional, decomposition into generalized eigenspaces. So then you work with each generalized eigenspace and employ that argument. If you take a generalized eigenvector V corresponding to a generalized eigenvector lambda, you push it with pi y V would be a generalized eigenvector corresponding to a different generalized eigenvalue. So after a finite number of steps, pi y to the power some number applied to that vector should be 0. Now you do that for each generalized eigenspace. And you are done. So ultimately you have this, that there exists S such that pi y to the power S is 0, and on the left side this is the S that we mean here. So that means this pi y to the power S h naught is going to be 0 because this operator itself is 0. And on the other extreme, by other extreme what I mean is, pi y to the power 0 hs, okay, so that is just hs. Now what we want to prove is, show that this hs is 0. And in this proof, that quantity A that I defined earlier, that would be used. So A is kind of secondary. I defined it first, but right now A doesn't have a role. A will have a role once we start proving this hs equal to 0. Okay, now what happens if once we prove hs equal to 0? So let's look at hs. So hs is hs is of course the expression for hr where you replace r by s, but then there is a change in the expression inside if you look at it carefully. So hs equal to
pi kj.
So that j is equal to minus s plus 1, s minus 1, and then you have pi k j. Now what is this? If you go to the definition, pi k
q to the power j.
j equal to something to something, so minus s plus 1 to s minus 1. And further, let's say you take out pi k inverse, you take out qj, then what you will have is pi k square minus
q minus 2j.
2j. Okay, q minus q inverse, it with a certain power it would come out of the product. So q minus q inverse to the power something, what is it? Twice s
Minus 1.
minus 1.
Pi k inverse power would be same thing.
Yeah, right. The same thing would happen with this also. Pi k inverse to the power something, so
2s minus 1.
2s
minus 1.
minus 1, and q here also with a certain power it would, you can bring it out. So this product really you can okay, L doesn't.
The sum will be 0, right? Q to the power q to the power j is from minus s plus 1 to s minus 1, so that sum would be 0, right?
0, but even if it's something else, so you don't even need to compute.
Okay.
It would be something, and then so main thing is that then what you get is something, then inside this product pi k square minus q to the power minus 2j, right? So pi k minus q to the power minus j, pi k plus q to the power minus j.
Yes.
So once you prove that hs is 0, what would follow is that this is 0.
This product is 0.
And then that would mean that the minimal polynomial of pi k would divide this. This in the sense that x minus q to the power minus j, x minus q to the power j
X
product, this, right?
x minus and x
Plus.
plus.
Right, so minimal polynomial divide this, and this polynomial on the right, it has distinct linear factors. So minimal polynomial of pi k will have distinct linear factors.
Yes.
So if we show that hs is 0, then the proof would be complete.
Yes.
What we wanted to prove initially, that the minimal polynomial is of this form, so that pi k diagonalizes. So the step that needs to be proved is hs equal to 0. And here so what will be proved is this for so basically this statement we need for I equal to s.
I equal to s.
And we have the statement for I equal to 0. Okay. And the steps in the proof is that you like so okay, I'll go to the next page and then so in the first step we have pi y to the power s h naught equal to 0, and what we want is hs equal to 0, which is pi y to the power 0 hs equal to 0. So the steps would be, so from starting from here one proves that this is 0, then that would give, so you go one step at a time.
Yes.
So to begin with you have this for I equal to 0, then you prove it for 1, then you prove it for 2. These are the steps in the proof, that's all. So you need this, you have this, so you have to go, I mean at least in this proof you have to go this way. So this is where that earlier quantity A would come into picture. So A was this pi y r pi y s times something, and now you need this computation. So x r y s equal to, I think this exercise I may have mentioned last time, I don't remember. If not, then so this also you have to do this computation, that is x to the power r y to the power s would be a summation where is the same expression. Everything is under this summation. I equal to 1 to j k, and then j minus r minus s plus I. So mean, of course, reaching this expression may be difficult, but once you are given this expression, for proving, you have to use induction. So first so this is for R and S, N. So if either one is 0, then there won't be anything to prove almost. So for XY, I mean for R equal to 1, S equal to 1, you prove it, and then just exhibit these two steps. Then will be done. And these two steps you use induction. Okay. So now if you go back to the expression for A, so A, the expression starts with pi x to the power R, pi y to the power S, right? So there you plug in this value. So this expression, but pi applied to this. So pi x R, pi y S. So the steps would be that, show that and okay, we have to go back to the expression for A again. So look at the expression for A and HR.
A and HR, yes. R S HR.
HR. So A is something, then HR, right?
A is pi x R, pi y is HR. No, sir. There, it is from J is equal to 1 to R minus 1, but HR is minus R plus 1 to R minus 1.
So there is a difference, right? So in A you have 1 to R minus 1, and here you have so it's not just something times HR, so it is more complicated. I think that would come out of the computation. Okay, so this, and then just a moment, I myself is getting confused a bit. What in A there was ace, right? Achha, okay, ace was there in expression for A. Fine. So then it's so see if you get this. Just a moment, I'm just looking at the computation and then getting slightly confused. So okay. So the confusion is the following. So what you want to show is for for 0 right, this is what we want to show. Okay, right, so I was again missing this crucial step in the proof. So assume that this is true.
Sir, where it is written? Maybe not updated.
Okay. So you have to show that pi y to the power s minus I hi is 0 for I between 0 and s.
Okay.
So you assume that this is 0 for I between, so for I equal to 0, it's true that we know. You assume that it is true for I between 0 and r, where r is something less than s. Or rather, make it this way. Where r is. So assume that it is true for I greater than equal to 0 but less than r, and now you want to show that this is true for I equal to r. s minus r hr equal to 0. Okay, so this is your hypothesis, and it is here that you introduce that quantity A. Okay, so now you make the computation. So A, if you just go to the definition of A, it is pi x to the power r, pi y to the power s, and then something. So here you substitute the computation on the left hand side, the exercise on the left. So you will get some expression, some big expression. So here you plug in this. Okay. So then if you plug in this, then what you would get is A equal to basically something times pi y to the power what you had to prove in this step, s minus r
hr.
Okay. And then
By
you compute it differently, you get 0. So so then the end result would be that these two would be equal. So on one side you will compute using the calculation on the left side of the screen, and the hypothesis here, this one, and here you will make the computation differently to get 0. Okay. And why is this 0? That is because the expression for A involves pi y to the power s.
Pi y
that
power
itself
s,
is
yes.
0. But in this right hand side, right part of the computation, you forget about that fact. You just do the manipulation, so expand everything and so on. Because when you expand on the left side of the screen, when you use this computation, y to the power s gets replaced with smaller powers of y. So that is the thing that is exploited here. So this part is computation, but it's good to go through this computation once, so you can just complete the. But conceptually, what is happening in the proof, that we have already seen in the previous screen. So h is equal to 0, then that means that a polynomial expression for pi k is 0, and that polynomial expression factorizes into linear factors. So the minimal polynomial also
has linear factors.
So V decomposes as the direct sum of eigenspaces of pi k. Pi k is diagonalizable. Okay. So next we have to, it does not give us what we want yet, so we have to still work a little bit more for that. So before we do that, so we won't start that proof immediately. We'll do something else before that. That will be useful. Okay.
we want to show that the direction of weight space.
That we have done, right?
Hmm.
That V is the
That-
direction of white spaces, that is complete, right? That proof is complete now.
That proof is complete.
But our goal is to show that it is a direct sum of irreducible sub-representations.
Yes.
So that proof we still need to do, that we will do a little later. So before that we will introduce a few more things. Okay. So yeah. So we have this associative algebra UQ SL2C. So I'll just okay. Let's use the shorter symbol. Let's write U. So on U, you take the left ideal generated by the element X and the element K minus lambda. Okay, so fix lambda complex.
Sir, updating is.
It's not updating. Okay, sorry.
Okay.
So I think previous screen we saw the entire thing. So yeah, on this screen I just started. So we have this algebra UQSL2C. Let's fix a complex number lambda. Now let's look at J lambda. J lambda is the left ideal generated by X and K minus lambda. So in fact J lambda is equal to Ux plus UK minus lambda. Okay. So this is basically all elements of the form AX plus B K minus lambda. AB belongs to B. So this is the left ideal. It contains X, it contains K minus lambda, and any left ideal containing X and K minus lambda has to contain this. So this is the one generated by X and K minus lambda. Now we look at the quotient vector space. Okay, so this will denote by m lambda.
Okay.
Now, what is happening in m lambda? M lambda is basically in U, you are identifying X with 0 and K with lambda, lambda times 1 or lambda. Quotienting by this ideal essentially means that, right? You are looking at the ideal generated by X minus 0, which is X, K minus lambda. So this is the identification you are making in U when you are forming this quotient. So, which means that these will give you form a basis for m lambda. So this is something, okay, we have not, so this you can try to prove directly. I think directly also it should be possible. The another way would be to, before going to the quotient, first to prove that for U, x to the power r, y to the power s, k to the power t, where r and s are and t is integer, because k and k inverse both are there. So this is a basis for u. Okay, so I mean, if you prove this first, then that earlier statement would follow more easily, but this can be shown separately also. And for proof of this statement or that statement also, I think you can use the list of irreducible representations that we have already. So typically, how one can show this is the following. So you have to show something like this, right? If you want to show that this is a basis, xr ys kt equal to 0 implies crst equal to 0 for all rst, and this is a finite combination. So you start with such a combination where you assume that all the coefficients are non-zero, because you can do that by ignoring terms with zero coefficients, right? So you start with a combination where all coefficients are non-zero, but the combination is 0, and then try to use an appropriate representation from that list. Okay. Now, by using one of those representations, what happens is you are now on a concrete vector space, you know their actions exactly, and then you try to show that one of these coefficients, whichever is convenient to show, one of the coefficients is 0. Then you will get a contradiction.
Similar to classical one.
Yeah, right. So it's the same. So in m lambda, then this would give you a basis, and now from the computations that you would have done, it's possible to write down the action of left multiplication by elements of Q. So what I'm trying to say is the following. See, this ideal J lambda, it's invariant under left. It's a left ideal, so it's invariant under left multiplication, right? So now U has a representation, natural representation by left multiplication on U.
Sir, not arbitrary.
So J lambda is an ideal that's left invariant under left multiplication. It's a left ideal.
And U is left multiplication on U.
Yeah. The second line, what I'm saying is, for U, you have this representation, natural representation. So it's a pi of x. So pi
Okay. X, yes.
Right. This natural representation we have on U. Now, since J lambda is invariant under this representation, so this would lead to a representation on m lambda. So So what would be that action? That is what we want to write down next. So this I'll write as an exercise. So the action of K on, so I'm using this to denote the image of y to the power j in the quotient. Okay, so this is 1. So this would be the action. Okay, let me go to the next page. Which page are we start? So let's write mj for this. Then what do we have? We have m lambda is equal to span of these mj's, and we have this representation on m lambda, namely pi k mj equal to lambda times mj, j greater than equal to 0, pi x mj equal to that number there, lambda, sorry, no, lambda 1 minus 2 0 equal to 0, and pi y mj equal to mj plus 1. So this gives a representation that you can immediately verify, and anyway there's no need to verify actually, because this lifts from a representation from that earlier representation, that left multiplication, right? So this is going to be a representation. So this is a module. This is a representation. This is a module. So this is called the verma module. So in fact, in classical case also, that in fact their verma module came first naturally. So this is an analog of that. We did not see it in the classical case, but maybe later at some point take a look. But this verma module in the classical case, so in the classical case it's very similar. So there you quotient u by
X and H.
Huh?
X and H.
H,
Okay.
H you identify with
Okay, H minus lambda.
Okay. And here it, instead of H you have taken K. Okay. Now let's look at this representation a little bit closely. So what is, so you have this basis, each one is an eigenvector for k, pi k. Pi y is that right shift. This is pi y. Then pi k, there's nothing. So basically it goes to itself. And so on. And
Pi x is left shift.
Pi x is so pi x is left shift with some coefficient, right? So because of that coefficient, there can be a little bit of extra complication here, in the sense that, for example, if that coefficient is 0, then there would be a break here, right?
Yes.
Then
Yes.
this element will not come to the left anymore. Okay. So that is something we need to find out.
Okay.
So let me delete the left side. Just a moment. Okay, so you want to find out if there is any break. That means you want to find out when this number is 0 or if this number is 0, right?
Yes.
So this
JQ cannot be 0.
huh?
JQ cannot be 0.
So
So we can ignore.
it cannot be 0. In fact, the numerator denominators cannot be 0 either. So only this quantity can be 0. So it would be 0 if and only if this quantity is 0. And that happens when lambda square equal to
Q to the power minus 1 plus j.
q to the power
Minus 1 plus j.
1 plus
No.
j.
2 into this.
2 into this.
So lambda equal to plus minus q to the power j minus 1.
Sorry. 2 j minus 1. So lambda equal to plus minus does not belong to this set,
Hmm.
then the coefficients are all non-zero.
Yeah.
Okay, so in this case, show that this module is simple, or equivalently the representation is irreducible. Okay,
Hmm.
and so this is in this case, show if lambda does not belong to plus minus q to the power n to, okay, that is number one. Number two, if lambda equal to plus minus q to the power n, then show the following, that okay, if when lambda is q to the power j minus 1, then where there is a break,
That
mj does not go to
mj minus 1.
So that means when lambda is plus minus q to the power n, then
mn plus 1 goes to 0.
sorry, not q, m n plus 1, mn plus 2, this is a submodule or an invariant subspace, so that it gives a sub-representation, right? Okay. Then I'll just make I'll stop a little earlier to no, I'll just I'll stop with two more statements,
Okay.
so which you can work out. So this is 3. This is again the same case. If lambda belongs to case, I can write more explicitly. If lambda equal to plus minus q to the power n, then only invariant.
Only invariant
Subspace or only submodule. I'm mixing up both the languages, representation and module. So only non-trivial submodule. Okay, then 4. M lambda quotiented by this.
Okay.
This is actually 3a, 3b you can write, because it's still under the same case, 3b, and this is 3a. Mn plus 1, mn plus 2, and so on. This is
1 to up to n. Okay.
N, sorry. Here I should be in plus minus. So depending on here whether you have lambda equal to plus
or
to the
minus.
power n or minus. So you get those irreducible representations as
the quotient.
Quotient modules of the verma module or homomorphic images of the verma module. Okay, so this is something that happens in the classical case also. So verma module itself is an infinite dimensional module, but any irreducible module can be realized as a quotient module like that. Okay, the other exercise that I'll stop with after stating this, I'll stop. This. So define this element, which is yx plus
Kashmir element.
Yes. Did I already write it down earlier?
No, sir. That was the classical one.
Okay. So this is an analog of that, and this would be there in the note also, but it's stated there also as an exercise. So but doing this is just some computation. So define this, and then show the following. So C is in the center of U. And 2 C. So by this, what I mean is the action of C on this verma module.
Okay.
So this is lambda Q plus lambda inverse Q inverse so on each verma module it acts as a scalar. Okay. And the third statement, compute ym plus minus. So these are the irreducibles. Okay.
Yes.
So we'll see that there also for each irreducible it acts as a scalar. And also once you compute, you'll see that those scalars are different for different irreducibles. So once you have an irreducible, if you just look at the action of this element, it is possible to determine which irreducible you are dealing with.
Okay.
So yeah, so I'll stop here. So you finish till here, then basically now we have everything that we need for proving complete reducibility. Okay. So the strategy there would be, now you have an element from the center, right? That means if we decompose the entire space, suppose we have a representation finite dimensional, we decompose the space into generalized eigenspaces of this element C. So each of those generalized eigenspaces would be an invariant subspace of the representation. So this is different from K or H in the classical case K. If you take an eigenspace or generalized eigenspace of K, that is not invariant under the representation.
Yes.
But for C, since it's the center, generalized eigenspace would be invariant under the representation. Okay, so we can, for convenience, we can decompose first into generalized eigenspaces of this operator phi C, and then work with each of those and decompose them into irreducibles. So that would be the strategy of the proof. Okay. And so this proof ultimately, once we finish, it would look a little different from the proof in the classical case, but then we can take a relook at the classical case. So we can basically, the proof that we are going to give here, that can be employed there also, but you need a little bit of modification in one place.
Okay.
So that we'll do next time. So let's stop here. So, you post anything there, and when you are done, just let me know.
Okay.
আর আরেকটাই হলো যে ওই নোশনের পেজটাতে ম্যাথের জন্য the other way is to, একটা তো আমি বলেছিলাম ওই রাইট সিলেক্ট করে নিয়ে দেন that option. The other way is to you just type and enclose with $.
আচ্ছা, $এর মধ্যে লিখলেই হয়ে যাবে,
অটোমেটিক্যালি করে নেয়, so that you select করার ব্যাপার থাকে না। মানে only thing is you মানে ম্যাথস পার্টটাকে কিপ ইট টু এ মিনিমাম, মানে অ্যাট লিস্ট যদি কোনো ইংলিশ পার্ট থাকে ওগুলোকে, ফর এক্সাম্পল তুমি যখন লাইন ব্রেক করছো, নিউ লাইন দিস দ্যাট, ওগুলো লেটেক্স ফাইল যখন কম্পাইল করছো দেন পারহাপস ওকে, মানে এখানে ইউ জাস্ট ট্রাই টু কিপ জাস্ট দ্য ম্যাথস পার্ট।
ওকে,
মিনিং আদার পার্ট ইউ জাস্ট টাইপ ইন নরমাল টেক্সট, ডলার দিয়ে এনক্লোজ করবে খালি, মানে এসেনশিয়ালি ম্যাথমেটিক্স সেই পার্টগুলো।
ওকে।